Hello and welcome back, and if you are new here, welcome, we are very glad to have you here. We are slowly, but surely developing a naming OCD, beginning from circular economy, where nothing is round, or going in circles, through AC signals, where nothing alternates, to PN junctions and diodes made of spatulas. So, before we lose it completely, let's address the proverbial elephant in the room. Spatulas are made from synthetic polymer, called silicone, spelled with E at the end of the word, whilst diodes and transistors are made from chemical element silicon. Of course, in this video, our attention will be devoted to chemical element silicon, which is building element for semiconductor components, such are diodes, transistors and similar. Another element, commonly used for semiconductor components is germanium. A quick introduction to a Danish physicist, Niels Bohr, and his model of atom is in order, before we proceed any further. In year 1913, Niels Bohr proposed a model of atom, wherein the center of the atom is nucleus, consisting of positively charged protons, and neutrally charged neutrons. Around nucleus, in various orbits, are negatively charged electrons. Although, some modern physicist heavily disputes this model of atom, especially notions regarding existence, role and behavior of electrons, but themselves are unable to provide any viable alternative to the proposed model, we have no choice but to accept current dogma, and continue with this model of atom. Atoms differ regarding number of protons and neutrons in nucleus, and electrons in orbit, starting from most simple hydrogen atom, consisting of one proton and one electron, to element called organosyn, a man-made, non-naturally occurring, synthetic atom, which has 118 protons, and 176 neutrons in nucleus, and 118 electrons in various orbits. There are many groupings and categorizations of atoms, regarding their various properties, starting from number of electrons in their most outer shell, through atomic mass, to surprisingly, even color. For our current interest, in this video, we will adopt categorization of atoms, in regard to number of electrons in their most outer shell. For our interest, we will cherry-pick a group of atoms that have from 1 to 8 electrons in their most outer shell. Number of electrons in outer shell is called valency. This is somewhat simplified definition of valency, but suffice to say, number of valence electrons determine how easy, or how hard, an atom combines with other atoms, by simply volunteering or receiving an electron, or more of them, to create a chemical bond. This sounds quite familiar to our story about copper atom, and its most outer shell, and that one electron, that is capable to easily leave orbit and jump to adjacent hole, and thus facilitate flow of current in conductors, right? We will return to valency story in just a bit, but for now, let's single out one silicon atom and see what is so interesting about its outer shell, and its valency electrons. The picture shows a model of silicon atom. Its nucleus consists of 14 protons, 14 neutrons, and 2 electrons in first orbit, 8 electrons in second orbit, and 4 electrons in third, our most outer shell orbit. This number of electrons in outer shell makes a story very interesting. Silicon atom has same affinity to either release all 4 electrons from outer shell, or to receive 4 electrons from a donor atom. This is due to fact that every atom is in its most stable chemical state, when its outer shell comprises of 8 electrons. So, to simplify things, our silicon atom is most happy, when it either receives 4 electrons from donor atom, so it fills its outer shell with 8 electrons, or when it volunteers his own 4 electrons to recipient atom, so it is left with 8 electrons in second orbit, which now becomes the most outer shell. Now, let's see what happens when two silicon atoms find themselves in close proximity to one another. Surprisingly enough, rather than one atom giving up all 4 electrons from outer orbit, and the other one receiving them, to complete its own outer shell, 2 atoms will combine their most outer shell and volunteer all of the 4 electrons from their own outer shells to now newly formed joint orbit, encompassing both atoms. Now both atoms have 8 electrons in their outer orbit, 4 original ones, and 4 joint ones, from the other atom. In this manner, 2 silicon atoms create strong bond, or to say more precisely, they form a crystal structure. Now, in real life, much more than 2 atoms create silicon crystal. Also, in this crystal structure, silicon atoms do not create bonds with other atoms easily. What is important to remember is that silicon atoms create strong bonds that require great amount of energy to break, thus silicon crystal is very stable at high temperatures. The temperature required to break silicon crystal bond is 1410 degrees Celsius. Disclaimer: model of atom, an animation depicting joint shell, shared between both atoms, is just a visual aid, to help you comprehend and visualize otherwise, extremely complicated and chaotic orbits of electrons that occurs in nature. They do not represent true-to-life depiction of naturally occurring processes in atoms. Now, germanium atom is comparable to silicon atom in a manner, that it also has 4 out of 32 electrons in total, in its outer shell orbit, with 32 protons and variable number of neutrons in nucleus, depending of type of germanium isotope in question. Same as silicon, those 4 germanium's valency electrons create strong bonds between germanium atoms, forming a crystal structure. Melting point of germanium crystal is 938 degrees Celsius. Both silicon and germanium are materials most commonly used to make semiconductor components. Another common classification for both silicon and germanium are as metalloids. Metalloids are elements that have properties that are intermediate between those of metals and nonmetals. They can also be called semi-metals. Some of the common properties of metalloids are, they have a metallic appearance, but are brittle and poor conductors of heat and electricity, they can form alloys with metals and covalent compounds with nonmetals, they tend to behave as semiconductors, meaning they can carry an electric current under certain conditions, but not under others. There is no standard definition of a metalloids, and no complete agreement on which elements are metalloids. However, the most commonly recognized metalloids are boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. Now, let's get back to valency. We have defined valency as number of electrons in most outer shell of an atom. We have learned that 2 atoms of most interest to us, silicon and germanium, both having 4 electrons in most outer shell. Now, 2 other types of atoms that are of particular interest to us, in our story about p and n-type materials, and p-n junction, are those with 3 and 5 electrons in their most outer shell. They are called trivalent and pentavalent atoms, respectively. What is most important about them is, that they have 3 and 5 electrons to create covalent bond with another atoms. A covalent bond is a type of chemical bond that involves the sharing of 1 or more pairs of electrons between 2 atoms. There are different types of covalent bonds, depending on how many electron pairs are shared and how evenly they are distributed. A single covalent bond involves 1 shared pair of electrons, a double covalent bond involves 2 shared pairs, and a triple covalent bond involves 3 shared pairs. Now, let's create silicon lattice. Let's assume that by some miracle of modern technology and magic, we can manipulate single atoms. The following can be equally applied to building silicon or germanium crystal lattice. For simplicity, we will use a silicon atom for our example. We will represent single silicon atom with gray circle, marked C, and we will only represent valent electrons in most outer shell with blue circles. Now, let's place a single silicon atom in the middle of the screen. In its most outer shell, a single silicon atom has 4 valent electrons that can form covalent bonds with another silicon atoms. Now, let's introduce 4 more silicon atoms, and put them in close proximity to first atom, in such a way that all atoms are close enough for their valent electrons to start making covalent bonds. What happened now is that each surrounding silicon atom formed one covalent bond with central atom. Each individual pair of silicon atoms now share 2 common electrons. As a result, central silicon atom now has 8 electrons in its most outer shell, and it is complete. This atom is now in its most stable condition, and it would take enormous amount of energy, in the form of heat to break covalent bond, that central silicon atom now has with surrounding silicon atoms. If we continue to grow our silicon lattice, by adding 8 more silicon atoms, those additional 8 silicon atoms will now create covalent bonds with previous 4 surrounding atoms. Now, we can continue to grow our silicon crystal lattice, but suffice to say, that now those previous 4 atoms, that were first surrounding original atom, themselves, now have a full outer shell, filled with 8 electrons, and are in their most stable condition. By adding only silicon atoms to our crystal lattice, we made an intrinsic semiconductor. An intrinsic semiconductor means that entire crystal lattice is made of only silicon atoms, with no impurities. Same goes for crystal lattice made from germanium atoms. This was depiction of how silicon atoms create crystal lattice in 2D plane. Of course, in real life, crystal lattice grows in all 3 dimensions. Nevertheless, the same rule for creating covalent bonds applies between valent electrons in most outer shell, for every single silicon or germanium atom. One of the most important things to notice about crystal lattice is that only atoms that are surrounded from all 4 sides in 2D plane, or all 6 sides in 3D space, are atoms with complete outer shell. They have created covalent bonds with adjacent atoms, and have 8 electrons in outer shell. In this state, called intrinsic semiconductor, our crystal lattice acts like insulator. Important thing to notice is that edge atoms are still incomplete. They still have free valent electrons in their outer shell. Now, those are the atoms that will play significant part in creation of N and P-type semiconductors. Now that we have created our silicon crystal lattice, let's see how P-type semiconductors are made. As previously mentioned, we are only interested in edge atoms of crystal lattice, so for the purpose of this part of the video, of our story about semiconductors and P and N-type materials, we will use just a snippet of the edge atoms. To create P-type semiconductor, we need to dope a surface of silicon crystal lattice with trivalent atoms. Trivalent atoms are those that have 3 valence electrons, such as boron, aluminum, and indium. For our purposes, we will mark trivalent atoms with number 3 for nucleus, and will color it red, and we will depict only most outer shell, and we will represent electrons with blue circles, as before. Now, doping is a technological process, where atom vapor is created, and surface of the crystal is exposed, for a period of time, to such vapor, in order to combine crystal's atoms with trivalent atoms. Visualize it as fog made of atoms, sliding over the surface of silicon crystal. Now, our trivalent atoms are in proximity of silicon atoms, and they can create covalent bonds with silicon atoms, but also, between themselves. As atoms on the surface of silicon crystal lattice only have 1 valent electron, to form bond with trivalent atom, the rest of 2 remaining electrons will create covalent bonds with other trivalent atoms. Now, each of surface silicon atoms is complete, with full complement of 8 electrons, but each of trivalent atoms now has 2 empty spaces, called holes, that are considered positively charged. We will mark hole with empty dashed black circle. You can repeat doping process as many times as necessary, in order to create p-type material of required specifications and characteristics. For our own demonstration purposes, we will add 2 more layers of trivalent atoms, making it 3 layers in total. Each time we add another layer of trivalent atoms, total number of holes increases, as there are not enough electrons in trivalent atoms to complete outer shell with 8 electrons. As a result, the more we dope surface of silicon crystal with trivalent atoms, the more positively charged it becomes, as number of holes increases. Extrinsic is just a fancy word for doped semiconductor. Now, let's see how we can create N-type material. Creating N-type material is in essence the same process as creating P-type material, but instead of surface of silicon crystal being exposed to vapor made of trivalent atoms, for creation of N-type material, we will expose surface of silicon crystal lattice to vapor made of pentavalent atoms. Pentavalent atoms have 5 valent electrons in their most outer shell that can combine with other atoms to create covalent bonds. Some of pentavalent atoms that can be used for N-type doping are phosphorus, arsenic, antimony, and bismuth. For our purposes, we will mark pentavalent atoms with number 5 for nucleus, and will color it yellow, and we will depict only most outer shell, and we will represent electrons with blue circles, as before. Now, doping is a technological process, where atom vapor is created, and surface of the crystal is exposed, for a period of time, to such vapor, in order to combine crystal's atoms with pentavalent atoms. Visualize it as fog made of atoms, sliding over the surface of silicon crystal. Now, our pentavalent atoms are in proximity of silicon atoms, and they can create covalent bonds with silicon atoms, but also, between themselves. As atoms on the surface of silicon crystal lattice only have 1 valent electron, to form bond with pentavalent atom, the rest of 4 remaining electrons will create covalent bonds with other pentavalent atoms. Now, each of surface silicon atoms is complete, with full complement of 8 electrons, but each of pentavalent atoms now have 2 free valent electrons that are unpaired. By repeating doping process, as many times as necessary, to create N-type material of required parameters and characteristics, we are adding layers and layers of pentavalent atoms, with each layer, producing more and more unpaired electrons, thus making N-type material negatively charged. Before proceeding to part of the video explaining formation of p-n junction, we have several very important issues to address. First, our depiction of doping process was meant for ease of understanding, and visualization of creation of covalent bonds, and not as depiction of real-life doping processes, as they occur in factories producing semiconductors. Second, manufacturing process of creating extrinsic semiconductors is very technologically complicated, and precise methods and materials used in manufacturing are often considered trade secret. Now, let's see how p-n junction is made. Previously, we have shown how p and n-type materials are made. A silicon, or germanium crystal is doped with trivalent and pentavalent atoms, in order to create n-type and p-type material, respectively. Now, let's see what happens when p and n-type materials are produced on a single piece of silicon crystal. Let's assume that by some manufacturing process, left side of silicon crystal is doped with trivalent atoms, and right side of crystal is doped with pentavalent atoms, simultaneously, with some barrier, separating 2 types of doping materials, preventing them to come in contact, before they reach silicon crystal. From what we have previously learned, we know that trivalent atoms will combine with silicon atoms, to create p-type material, leaving residual holes in process, thus making left side of silicon crystal more positively charged. In the same time, pentavalent atoms will combine with silicon atoms on the right, creating n-type material, leaving residual electrons in the process, thus making right side of silicon crystal more negatively charged. However, this is not the end of the process. Have in mind that we still have a number of free trivalent and pentavalent atoms that have not combined with silicon atoms in crystal lattice. Also have in mind that trivalent atoms have 3 valent electrons to give, and that is the exact same number those pentavalent atoms need in their most outer shell, to complete their shell with 8 electrons. Now, here comes a magic of creating p-n junction. Now, some of those uncombined trivalent and pentavalent atoms will combine with each other, thus completing both of the atom's outer shell with 8 electrons, leaving them neutrally charged molecules. Furthermore, not only that combination of trivalent and pentavalent atoms created neutrally charged molecules between p and n side of silicon crystal, it also created physical barrier that will prevent any further recombination of atoms from p and n type side of silicon crystal. But wait, there is more. There is another emergent property of this entire process. Generally speaking, left side of our silicon crystal is positively charged, and right side of our crystal is negatively charged, with middle that is neutral. When on one side we have positive charge, and on opposite side we have negative charge, an electric field is developed. Electric field is marked with capital letter E, and since it is a vector, it has its direction, from positively charged side to negatively charged side, and it is measured in unit called voltmeter. Usually, it is depicted with directed straight parallel lines, and number of lines indicate intensity of electric field. The barrier that has formed between p and n type side of silicon crystal is called p-n junction. Dimensions of p-n junction, primarily its width, determine parameters and characteristics of semiconductor component. Now, there is one more thing we have to address before we conclude our story about p-n junction. If you have paid close attention, in the part of the video where we talked about silicon atoms, and creation of silicon crystal lattice, we mentioned that energy required to break covalent bonds between silicon atoms in the lattice is great. However, the story differs a little bit with dopant atoms. Dopant atoms are those trivalent and pentavalent atoms, used to create p and n side of our extrinsic semiconductor. As we have previously seen, those dopant atoms have many extra holes and electrons on their respective sides, and only thing preventing them from moving through extrinsic semiconductor, and thus creating electric current, is barrier of p-n junction, or more precisely said, an electric field developed as a result of creation of p-n junction. We have previously mentioned that electric field is a force developed as a result of proximity of positively and negatively charged particles separated by neutral barrier. We know from physics that every force can be countered with equal or greater force of opposite direction, so it is in our case. In order to counter electric field of p-n junction, we need to apply force, in shape of voltage, in amount of 0.7 volts or higher. When such voltage is applied across terminals of our p-n component, potential that is given to valent electrons in n side of semiconductor, is enough to overcome the barrier of p-n junction, and all uncombined valent electrons from n side of extrinsic semiconductor, are now strong enough to cross the barrier, now with electrons from the barrier itself, being a facilitator of such electrons' movement. In case germanium is used as intrinsic semiconductor, after doping, the voltage needed to overcome p-n junction formed in germanium-based extrinsic semiconductor, is 0.3 volts or higher. In next episode of this season series, we will talk more about diodes, bias voltage, and roles diodes play in electric circuits. Please, before you leave, show your appreciation by liking this video, sharing it, leaving a comment, and consider subscribing. Thank you, and see you next time. Bye.